Hello everyone, I'm Mulgita. Today I will show you how to design reinforced concrete column. As you know, reinforced concrete column may be classified as short or slender according to slenderness limit. Design step is almost the same, but slender column considered second order effect. According to European code, second order effect calculate based on nominal stiffness and nominal curvature method. For today, I will show you how to design slender column based on nominal curvature method. On the next, I will show you how to design short column as well as slender column based on other method, nominal stiffness method. So don't forget to like, comment, subscribe and click the button to be familiar with me to get more knowledge easily. Well, let us start. Well, design the brushed column. The column may be brushed or non-brushed according to its support. If it is subject to the following loading as shown in figure 1.1 here, 2000 kN it is axial force diagram. 150 kN and 300 kN are bending moment diagrams for serviceability limit state and ultimate limit state. The column has total length of 6 meters. Its support condition is according to figure 1.2 here. Fixed. The material properties are given as C2530 for concrete and S460 for reinforcing steel. C2530 mean FCK or characteristic strength of concrete is equal to 25 megapascal and S460 mean FYK or characteristic strength of reinforcing steel is equal to 460. If the column is slender, compute the total design moment using nominal curvature and nominal stiffness method. In this video, I will show you on the nominal curvature method. On the next, I will show on nominal stiffness and the difference of those methods. Okay, use 400 by 400 mm. Creep coefficient is equal to 2 and modulus of elasticity is equal to 200 gigapascal. These all are about the question or the problem to design the brushed column. We have 5 major steps. The first one is material data. Basically, we have two materials to construct reinforced concrete column. So, we should study the property of those materials, concrete and reinforcing steel. The second and the third are focused on slenderness. Those are used to determine whether the column is short or slender. The fourth one is calculate eccentricity and design moment. The fifth one is detailing. So let us start. The first one is material data. FCD, design strength of concrete, which is equal to 0.85 times FCK over partial safety factor. FCK is characteristic strength of concrete. Since we have C2530, characteristic strength is equal to 25. So the value is equal to 14.166 megapascal. FYD, design yield strength of reinforcing steel, which is equal to FYK, design characteristic strength of reinforcing steel. It's given 460 over partial safety factor for reinforcing steel 1.15, so 400 megapascal. Modulus elasticity of steel, which is equal to 200 gigapascal. It is usually modulus elasticity equal to 200 gigapascal. Let us see the second one, slenderness. Slenderness is equal to L naught over I. But the point is how to calculate L naught and I. L naught is equal to 0.5 times L. The value of L naught is vary according to its support. I will show you how to calculate L naught. Okay, since we have the support condition is fixed, we use L naught is equal to 0.5 times L. Let us see. 5.8332 slenderness and effective length of isolated member. It is error code. So the slenderness ratio is defined as lambda is equal to L naught over I. L naught is equal to effective length, I is equal to radius of gyration. So how to calculate the value of L naught? Let us see our condition. Fixed. L naught is equal to L over 2. So we have L naught is equal to 0.5 times L. So according to its support, you can calculate the value of L naught. In our case, L naught is equal to 0.5 times that of L. So 3000 mm. I, radius of gyration, which is equal to root of moment of inertia over area. I is equal to h cubed over 12. A is equal to b times h. It is obvious. So radius of gyration is equal to 115.470 mm. So lambda is equal to L naught over I, which is equal to 25.98. Well, the third one is check slenderness limit, which is equal to 20 a bc over root of n. But how to calculate the value of a, b, c, and n? A is equal to 1 over 1 plus 0.2 power f. 1 over 1 plus 0.2 times 1, it is the value of power f, which is equal to 0.833. But how to calculate power f? Simply, power af is equal to 0 if it satisfies those conditions. Final creep coefficient, in our case 2, less or equal to 2, it's okay. Our lambda, as previous, 25.98, less or equal to 75, it's also okay. But the third one, MOED, design moment 300 kilonewton meter over NED. It is design axial load, not greater or equal to that of H400. So it is not okay. So how to calculate power AF? Which is equal to final creep coefficient, in our case 2, times movement in quasi-permanent or serviceability limit state 150 over design movement, or in ultimate limit state 300. 2 times 150 over 300, which is equal to 1. It's here. B is equal to 1.1. But the formula is equal to, the formula is B is equal to root of 1 plus mechanical still ratio. But we have no any data related to that of mechanical still ratio. So it is recommended value 1.1. So the third one is C, which is equal to 1.7 minus Rm, ratio of moment, which is equal to 300 over 300. It's given, or since we have uniform bending moment 300 kilonewton meter, so the value of 0.7. N, which is equal to NED, it's design axial force 2000 kilonewton over AC, area of concrete 400 by 400, and FCD it's calculated as previous 14.166, which is equal to 667, which is equal to 0.88235. So lambda limit is equal to 20 A B C over root of n, which is equal to 30.657. The point is here, since lambda, our value lambda is equal to 25.98, greater than lambda limit 30.657, so slender column, we consider second order effect. Unless otherwise, it will be short column, so no need of second order effect. But in our case, since lambda greater than lambda limit, we calculate second order effect. The fourth one is eccentricity. We have three types of eccentricity for slenderness column. The first one is accidental eccentricity. It is due to imperfection or low workmanship, which is equal to EA is equal to L naught over 400. Our L naught value is equal to 0.5 times L over 400, which is equal to 7.5 mm. Okay, equivalent first order eccentricity. EE, which is equal to maximum of those value 0.6 EO2 plus 0.4 EO1 and 0.4 EO2. But how to calculate the value of EO1 and EO2, which is equal to MO2 over NED and MO1 over NED. How to differentiate the value of MO1 and MO2? In our case, we have uniform load 300 kilonewton meter. So EO2 is equal to MO2 over NED, which is equal to 300 times 10 raised to 6 over 2000 times 10 raised to 3, which is equal to 150 mm. EO1 also 150 mm. So E is equal to maximum of those value 150 mm. E is equal to 150 mm. Well, the next one is second order eccentricity. The second order eccentricity is calculated based on nominal curvature and nominal stiffness method. But in this case, we calculate the second order eccentricity based on nominal curvature. On the next video, I will show you how to calculate based on nominal stiffness method. Okay, it is equal to 1 over r into L naught square over c. But c is equal to 10 since it is constant cross section. For constant cross section, c is equal to 10. It is recommended value. So L naught is equal to 0.5 times L, but the only unknown is equal to 1 over R. 1 over R is equal to K power 1 over R naught. K power is equal to 1 plus beta power AF. 1 plus how to calculate beta? Beta is equal to 0.35 plus FCK over 200 minus lambda over 150. FCK is equal to characteristic strength of concrete. In our case, C25, which is equal to 25, and lambda is equal to 25.98, calculated as previous. So beta is equal to 0.3018. So K power is equal to 1.3018. How to calculate 1 over R? 1 over R is equal to EYD over 0.45 effective depths. EYD is equal to 0.002. It's obvious. Over 0.45 times effective depth. Effective depth is equal to 400 minus 25. It is concrete cover. Minus 12. If we assume 24 diameters, the deformed bar, so 24 over 2, 12. Minus 8. It is stirrup. So 355. Effective depth is equal to 355. So 1 over R naught is equal to 1.25196 times 10 raised to minus 5. So how to calculate KR? KR is equal to NU minus N over NU minus N balance. N is equal to, calculated as previous, 0.88235. N balance is equal to 0.4. It's the recommended value, but the unknown is NU, which is equal to 1 plus mechanical steel ratio. The question is here, how to calculate mechanical steel ratio? We have no any idea about the area of reinforcement, so we don't know any hint on mechanical steel ratio. So it is by trial and error method. Okay, for first iteration, take E2, which is equal to 0. So E total is equal to EA plus EE plus E2. 7.5, 150, and 0. E total is equal to 157.5 mm. So design moment MSD is equal to axial design load 2000 kilonewton times E total is here. So 1 over 1000 mean to change millimeter to meter. So design moment is equal to 315 kilonewton meter. So VSD is equal to NSD over FCD BD. It is the same as N, 0.88235. Okay, MSD is equal to MSD over FCD BD square. MSD is 315. FCD BD square. So MSD is equal to 0.345. By using VSD, MSD and D prime over D, which is equal to 0.1, we can determine the value of mechanical stress ratio by using design chart. I will show you how to determine mechanical stress ratio from those points VSD, MSD, and D prime over D. So mechanical stress ratio is equal to 0.85. N is equal to 1 plus mechanical stress ratio 1.85. Kr is equal to Nu minus N, Nu minus N balance. Nu is here, N is equal to 0.88235 as previous, and the balance is the recommended value 0.4. Kr is equal to 0.667. 1 over R naught is calculated as previous here. 1 over R is equal to Kr, K power 1 over R naught. So E2 is equal to 1 over R here, L naught square over C, which is equal to 9.78 mm. In this case, E2 is equal to 0. But after first iteration, the value of E2 is not 0. It is design chart for column. The column design chart may be uniaxial or biaxial. It is for uniaxial since it is in 2 row, not surrounded in 4 row. So the first step to determine mechanical stress ratio is determine h prime over h or d prime over d. In our case, almost 0.1, so we select this design chart. EY is equal to 0.002, AS total is equal to 2A because into row mu SD and VSD. It is the formula of mu SD and VSD. So we calculate mu SD and VSD. In our case, VSD is equal to 0.88235. VSD is equal to 0.88, which means 0.5, 0.6, 0.7, 0.8. Then 0.88 mean 82, 84, 86, 88 around here. So it is the value for VSD 0.88 here. Okay, the next is mu SD 0.347, 0.0001, 02, 03. Then 0347, which means 0341, 2, 3, 4, almost 5 here. So intersection point is here. This parabolic line is mechanical stress ratio. It is 0.0, 01, 02, 03, 04, 05, 06, 07, 08, 09. It is between 08 and 09, around 0.85. So mechanical stress ratio is equal to 0.85. For second iteration, E2 is equal to 9.64. E total is equal to EA plus EE plus E2. The only difference is 9.78. So E total is equal to this. It's the same step from previous. VSD is here, MSD is different because E total is different. So mu SD and VSD, mu SD and D prime over D. The mechanical stress ratio will be changed because the value of mu SD is slightly changed because MSD is changed. So the value of mechanical stress ratio is equal to 0.925 by reading from the axial chart mu SD, VSD, H prime over H. So around 0.925. So n is equal to 1 plus mechanical stress ratio as previous KR is equal to 0.6837. 1 over R is as previous. So 1 over R is equal to KR K power 1 over R. The only difference is KR. So the value is here. E2 is equal to 10.0286 mm. For third iteration, take E2 is equal to 10.0286 mm. It's calculated as previous. So E total is equal to first order eccentricity, accidental eccentricity 7.5, first order eccentricity 150, and E2 this value. So E total is equal to 167.5286 mm. So the SCD is as previous. MSCD is slightly different because E total is different. So mu SD also different, 0.3695. Using those values, VSD, mu SD and D prime over D is equal to 0.1. Mechanical stress ratio is equal to 0.925. This iteration covers similar mechanical stress ratio 0.925 because on second iteration, mechanical stress ratio is equal to 0.925, and third iteration also 0.925. On second and on the third, mechanical stress ratio is the same, so our mechanical stress ratio is equal to 0.925. Unless we proceed to fourth, fifth, sixth, eighth iteration until the mechanical stress ratio is the same. Well, how to calculate AS total? AS total is equal to mechanical stress ratio 0.925 B times D over FYD 5241.679, but it's arranged in two rows. A is equal to AS total over 2, 2620 0.8395 mm. Check with maximum and minimum reinforcement limits. According to European code, S min is equal to maximum of those values 0.1 2000, this is NED, over 400 5 mm, 500 mm square. 0.002 AC 320 mm. It's okay. S maximum is equal to 0.08 area of concrete 12,800 mm. Our A value is between those values, so it's okay. Well, lastly, detailing. Assume diameter 24. For one diameter, area of steel is equal to pi d square over 4, 452.39 mm. So number of bar is equal to AS over AS. Our AS is equal to 2620.8395. Small AS is equal to 45239 is equal to 5.79, around 6. So it's arranged 6 diameter 24 and 6 diameter 24 like this. It is 400 by 400 section. This all are about how to calculate or how to design reinforced concrete column. Well, symbol with their representations. Thank you for watching.